Hello. Today I would like to continue from the previous class, lesson 4, which we have started to talk about the Heisenberg uncertainty principle. But today I would just give a brief example how Heisenberg uncertainty principle works. But before we go to that point, just to wrap up what we have previously talked, first point that mechanics deals with the atomic and subatomic scale. So when we make a measurement of subjects or object found on atomic or subatomic level, there always exists amount of uncertainty. So for this specific measurement or quantity that we are looking to find, there is always amount of uncertainty. So in fact, there is a limit how precisely this measurement can be made, and this is exactly what is we are meaning about Heisenberg. It's about the uncertainty. So this is just a practical hypothesis example. This is the electron in the path of the light, which is the photon, or I mean phonon, and this is light generated by some source. This is the observer. To let him detect and see the electron, there must be a collision happen here, and there is some transferred amount of energy and momentum will transfer from this light into the electron, and this is has proportional relation. As the light carried energy and momentum increase, so the amount of transferred energy to electron will be increase at the same time. So to know the electron position, we need to apply very short wavelength of phonon light, knowing its momentum and energy, which leads the electron to move with very high velocity, which will change the electron position. The position may be known at that specific position only. This uncertainty is knowing the position and the momentum at the same time is the basis of Heisenberg's uncertainty principle, and Heisenberg uncertainty principle is expressed at this equation, and we have talked about that this equation before. This is mainly h bar, which is the constant value, and it equals this value, which is joule by second, is a constant value. So some points about this equation. This equation tells us that the more precisely we know the position of that object, the smaller delta x. The less precisely we know the momentum, the greater momentum gradient b of x. So because this is constant value, so if this is higher, this has to be lower, and this is, if it's higher value, this has to be lower, because the equation has to keep constant value. Of course, I mean, from this point, that is impossible to measure at the same time delta x and delta b at the same time, but of course it doesn't mean that we can't make a precise individual measurement. We can, for example, determine the precise position of an object at some instant in time, but then the momentum would be completely unknown. This means we would have no way of knowing the future position of the object or the electron. The reason an electron doesn't have precise location of momentum, it is because its dual nature. That means it has the wave and particle nature at the same time. The practical point in this class today, we are starting with this example. Like, suppose we have a moving electron travels over x direction with velocity 8 multiplied by 10 up to 8 meter per second, and if the electron velocity measured at a precision value by like 0.3%, which is 0.003, then you have to calculate the maximum accuracy with which the position of electron would be measured at the same instant of time. So within this condition, this velocity, and this is precision that we calculate the velocity, we have to calculate the maximum accuracy with which the position of the electron could be measured. So we have to calculate delta x. Known that this is the known value, has to be known like the electron mass, and this is the h bar. Applying the Heisenberg uncertainty equation, from this one we have to calculate delta of x. So delta of x is mainly the uncertainty of the position of electron on x-axis. Just simply we place delta of x equal h prime divided by gradient of momentum, and for non-relativistic momentum, it's simply like momentum equal mass multiplied by the velocity. So since we are dealing with electrons, so it's mass of electron multiplied by the change of the velocity of electron. So the change of the velocity of electron can be also known as the uncertainty of the electron velocity. So if we are multiplying this value by mass of the electron, we can get the uncertainty of the momentum of the same electron. So this is the momentum. So if we are calculating the uncertainty of the velocity and multiply by electron mass, we can get the uncertainty of the momentum. So you have this value and you have the constant value. So the remaining is the uncertainty of the position of the electron on x-axis can be evaluated as this equation, meter per second. So this is the uncertainty of the position of electron on x-axis evaluated to be 4.8 up to 10 to minus 11 meter per second. Thank you.